I am going to talk about something a little bit different. I will caveat this presentation by saying I am not a machine learning person. My background is actually cryptography. And the company that I work for, ISARA, actually is focusing on a different area of the whole quantum sphere. We're looking at the security aspects of quantum. We're a Waterloo-based company. We're coming up on 6 years old, about 45 of us right now in sort of the Waterloo area. And we started with a focus on this problem of how do you ensure that companies can protect themselves from some of the interesting side effects that quantum computers will bring in the future then. We typically work very much in sort of North America, Europe, working with automotive companies, companies doing security infrastructure. But for this talk, I think it's really helpful to kind of start off with a bit of a level set. And I think what's useful is that a lot of these pieces have come up in the previous two presentations then. There's all this great work going on around the world in building quantum computers. But we're kind of still in early stages. So Paul was talking about, for example, that holy grail of getting to fault-tolerant quantum computing. And I think it's helpful to kind of put this in the context of what we went through in digital computing. If you think back to the early days, Adam mentioned, some pictures from IBM of showing, a few people wheeling a multi-hundred kilo computing device into a room. That was sort of those very early days when you didn't have RAM like we think about it today, where I just go down to a store and pick up a RAM chip to put in my laptop then. We didn't have machines that could run for months without needing to be rebooted then, because memory was coherent. So there was no problems with your RAM ceasing to be useful and having to be rebooted, removing power from it then. We have this consistent way of representing computation, the transistor on digital computers we have, but we don't have that yet for quantum computers. We are working through those stages, and Paul was talking about with Xanadu focusing on photonics, companies like IonQ looking at trapped ions, superconducting qubits were mentioned, silicon-based qubits. All this work is going on around the world around what are those sort of basic building blocks for quantum computers going to be, and then solving all of those system engineering problems that we need to go along the way in order so that we can put all of these pieces together into that fault-tolerant quantum computer. And I don't need to spend time on why people want to do this then. Machine learning is one great aspect of it then. But this is a worldwide drive happening right now. And what's interesting about it is, we really see numbers, 5 to 10 years to where we really have quantum computers that can solve some really cool problems. One of the interesting things to think about with quantum computers is that one of the first really neat problems that they can solve is how to make quantum computers better. So we have hopefully get to this point where you have a reinforcing loop where computers get better and better because you can use the current computer to make the subsequent one more efficient and more powerful. But I wouldn't be here if all quantum computers did were solve great and fun problems. I think Paul actually mentioned that one of the things that quantum computers are really good at as well is solving certain math problems. And one of the math problems is unfortunately underlying all of the mathematics that we use on the internet today for protecting information. This is known as Shor's algorithm. Interesting sort of side note, we don't have very many quantum algorithms. So true quantum algorithms. We have things like Shor's algorithm, we have Grover's algorithm, which I'll talk about in a second. We have a few other ones, but then we've gotten really good at using those core algorithms to build up all of this functionality on top of it then. So plug it with the conversation before about getting more people trained up in what are the things that you can do with quantum. That's because maybe it'll give us more algorithms so we can solve other cool problems with quantum computers. But Shor's algorithm, invented by Peter Shor, it's really interesting because it solves this math problem called the hidden subgroup problem, which you can actually take what's known as the RSA problem and the elliptic curve Diffie-Hellman problem and reformulate them in that way, in such a way that you can use Shor's algorithm to efficiently solve those problems. And this is important because what that means is that when you go and connect to Amazon via your phone to make a purchase, what's happening under the covers is that you're doing maybe an elliptic curve Diffie-Hellman key exchange between your phone and the Amazon server to agree upon a key, and then that's what's protecting your credit card information. What quantum computers using Shor's algorithm will be able to subvert that. So we have challenges, and I'll get into what some of those implications are, but because of how efficient Shor's algorithm is, it doesn't just mean that we can say, well, let's make our ECC keys bigger and then we're fine. We actually have to change entirely what we're going to use as a result of this, this algorithm. The other algorithm that we care about in the quantum world is something called Grover's algorithm. Grover's algorithm, of course, being very important also in the machine learning space. But what Grover's algorithm does is, of course, unstructured search. Where we use that in the crypto world is that one of the ways to attack a symmetric key algorithm is if you have 1 million keys, you just start trying out all the possible keys till you eventually find the right one. Once you have the right one, then you can decrypt the information then. Grover's algorithm purports to give you a much more efficient way of doing that, and has a square root speed up on the key size associated with those algorithms then. Now, we're not going to worry about Grover's algorithm in the context of this talk, because the reality is that actually implementing Grover's algorithm and implementing attack on, say, something like AES using a quantum computer is a lot more expensive than it sort of smells like when we're looking at it from this perspective here. So, as long as you're using AES keys that are big enough, then we're fine. We don't need to worry about this too much. But Shor's algorithm is the real problem that we need to think about here and how this affects our systems. And one of the things that we've been very, very good in the IT industry over the past, over 40 years now, RSA algorithm was created in 1977. The Diffie-Hellman was at the same time frame. Elliptic curves were 1983. So we're well over 40, coming up on 45 years that these algorithms have been around. And because they solve certain problems, confidentiality, authentication, identification, so well, we've put them everywhere in our systems. Even when you have a Bluetooth headset and you connect it to your phone, there is a public key exchange which goes on in the Bluetooth connection to authenticate the headset to the phone. Like, these are everywhere. And so the scale, when we start to think about making changes to this infrastructure, is huge. And also when we look at it like a modern IT environment, they have such a mixture of services, systems that they run themselves, systems that they've created themselves, maybe through their own IT department or outsourced, systems, of course, that they buy from someone and they just run, things that host themselves, things that are on premise, or things that are out in the cloud. This mixture complicates the transition that organizations are going to have to go to then. And something that organizations aren't very good at is knowing about what crypto they actually have in their environment. You think that for something that's so important, cryptography being plumbing that we use for protecting information, that every organization would have the equivalent of a spreadsheet somewhere that would talk about what crypto they have, where they use it, how strong it is, how they change it. And the reality is most organizations don't, because we haven't had to worry about this. We've gone through crypto changes in the past. We've had to change hash functions. We've had to make symmetric algorithms stronger and bigger, and sometimes public key algorithms make them a little bit bigger. But we've never had to do such a large-scale change that will be driven by an event at some time in the future coming up then. So there hasn't been this need in organizations to have this type of inventory then. So, we're lucky enough to talk to a lot of CIOs about how they think about cryptography. And this is a message that we hear over and over again, is sort of a lack of awareness even of how crypto fits within their overall environment. And then more importantly, how are they going to go about making changes to it? How are they going to change the systems that they're responsible, and then changes to the systems that whose throat are they going to have to choke in order to get the OEMs to make the changes that they need for the environment then? So if I leave you with one takeaway from this whole discussion here, is that your organization needs to start thinking about how you're going to be ready for cryptographic changes and becoming what's called quantum safe. And this is a great time to start thinking about it then. You don't need to make changes today, but you do need to start thinking about this. So if you're going to take away one thing, take that away from this discussion. So let's focus on a couple of very specific items then. The crypto world can seem so abstract that it almost goes outside of anything that we need to think about on a daily basis. So let's focus on three key areas that are important for us to think about within your organization. Number one, be future-proof communication. So this is confidentiality, things you need to keep secret. Number two, authenticated software updates. So how do I know that the software that's running on my laptop actually came from Apple? How do I know that what's running in my car is actually coming from the car dealership or coming from the car manufacturer? And finally, identity and access management changes then. I'm not going to spend time on that last one here just due to time. But if you think about large organizations that use public key cryptography, and especially ones that use things like smart cards or other ways of like physical tokens for identifying their users, all of that is based off of public key cryptography, and all of those are going to need to change. And those systems have this annoying tendency of fitting into so many different applications deployed in your environment that the IT migration problem dwarfs the math problem that we have to think about then. But let's go through the first two here in a little bit more detail. So what is this future-proof communication problem? So let's use an example because all of us are working at home. When you're connecting into your organization, it's very common to use a VPN. This could be using like a web VPN. This could be using like a traditional like Cisco style IKE style VPN, but this is just a remote way to connect into, say, your organization. And all of them look sort of the same if you squint at them hard enough. Step one, after you've actually connected, is for the two parties to, one, identify who they are. So I'm Mike, I'm connecting into my ISARA network. We prove this to each other using often certificates or things like that. And then number two is we need to decide on what's the key that we're going to use. What's that AES key that we're going to use for encrypting all the communications? Well, we do that doing a public key exchange. So we're going to send, maybe I'll send my elliptic curve public key over, and then the server sends their elliptic curve public key over, and we do a Diffie-Hellman exchange, and then out pops at the end an AES key that we can use then. And then going forward, this is the data exchange side. We just, Bob's your uncle, all the communications happen and they're encrypted. So who cares? Quantum computers that break crypto aren't here today. So why do I need to worry about this? Well, suppose I have information that I need to be protected in 10 years from now. It's not going to be something like, what am I going to have for lunch, or what's a specific stock trade that I need to do this week. But think about longer term secrets, information around long-term product plans, trade secrets associated with organizations. Those can traverse these types of connections because of the security that's there. But if we look at what's happening, all of this is actually happening over the internet. So that means the handshake happens on the internet, followed by the data exchange. And we know that there are organizations around the world who are actually storing encrypted internet traffic. And the reason they're storing that encrypted traffic is so that later on, let's say if they have a machine like a quantum computer that can break that handshake, then they can go back and retrospectively read those communications that went on in those targets. So if you have information today that you're sending on the internet that needs to be safe sometime after a quantum computer that can break, say, RSA is around, then you have an ongoing data breach. So this is sort of this planning step that organizations need to think about in that risk mitigation is, what things do I have? How long is my information need to be protected for? And what are the steps that I'm taking to make sure that I am ensuring those level of protections there? And luckily there's solutions, and we'll get to solutions a little bit later on there to help achieve this. The second scenario is around authenticated software updates. So, as I mentioned before, I'm in Waterloo. Around us, it is very flat. And so if you go out into sort of more the farmer's field area, you'll see, especially going out towards the lakes, you'll see a lot more things like windmills. What's a windmill? It's effectively an IoT device. It's a really big IoT device, but it's an IoT device where if someone's doing work on it, they're going to wear a parachute on their back. So it's a durable, it's connected IoT device, but it's difficult to do changes to it then. So of course, things like software updates, especially over-the-air software updates, are really important to, one, make sure that what's running on that machine, maybe that's a vehicle, is what it says it's going to be. And number two, providing a cost-effective way of actually making those software changes there. If we think about from our laptop, we're just used to the fact that Windows will do Windows Update while we're asleep at night, or Apple will do the same thing for updating Mac OS. These are all things that we've grown and relied upon there. But all of those focus on, are based off of the fact that there is a root of trust built into your machine, which is a public key. And that public key then is used to check a signature on software when it comes down to your machine to verify that it hasn't been tampered with along the way. Well, quantum computers will allow someone to impersonate that root of trust, and then if they wanted to, put software onto your machine that you don't know about then. So, of course, we need to think about, we need to fix this type of problem before a quantum computer comes along that can do that type of impersonation. So the question is when? When do you need to worry about this? And again, it depends on your use case. If we're thinking about your mobile phone, you don't need to worry about this today. Your mobile phone manufacturers will solve this problem over the next 5 to 10 years because we're not there yet, as I've said, around a quantum computer that can break commercial crypto. But when do we need to care? So I'm going to use a vehicle because vehicles have nice time frames to talk through something like this. So step one, when do we worry about quantum computers? Well, the estimates that we hear in the market are everywhere from 2026, which is way too early for a quantum computer that can break commercial crypto, or out to say like 2030, which is a date that NIST in the US, for example, is using for when quantum computers could break, like RSA 2048. We've heard this from IBM and Microsoft as well too. So this bubble in here seems like a good one to focus on for when your system, if it relies upon quantum vulnerable algorithms, would be at risk then. So let's imagine a car that's going to be on the road in 2035. So this car, it's going to be fully over-the-air software updatable. We know that kind of 2023-ish is when a lot of the car companies are focused on making sure their fleets are OTA software updatable, because this is around $33 billion in cost savings and revenue opportunities that the automakers are focused on. Now, car on the road in 2035 most likely came on the road in around 2023, because cars on average are about 10 to 15 years on the road. That means a car on the road in 2035 also has about a 6 to 8 year long design cycle. So if it's going to be on the road in 2035, it actually started production about 3 or 4 years ago. So if I'm worried about something existing after a quantum computer is around that can break commercial crypto, in the case of a vehicle, I actually need to start worrying today in my design cycle to make sure that I'm ready for this type of threat. So luckily, this isn't a case of, it's all doom and gloom and that we can be worried then. There are different solutions available for how to deal with this specific problem here. And we'll talk about 2 of them. Now, I'm going to give a bit of a caveat at the beginning. My background is math, so I'm going to focus on the math solutions then. You can basically split the solutions up into 2 areas. So one bucket is quantum key distribution. The other bucket is quantum safe cryptography. Quantum key distribution is this idea of let's use photons and share them between 2 parties. In crypto, we always say Alice and Bob. So share photons between Alice and Bob, and based on the effectively orientation of the photons, then that's how I can communicate ones and zeros. What I'm doing is I'm communicating quantum states between 2 parties. And the reason that we do this is because of a really neat physics property. If I share quantum states between 2 parties, and Eve, that's always the eavesdropper in crypto literature, if Eve views the system while the communication is happening, I can actually detect that. So there's eavesdropping detection built into this channel. So this is cool. Well, that's a really great idea then. So quantum key distribution gives us a potentially great properties of having a channel that no one can eavesdrop on, or at least we can detect when someone eavesdrop on it then. Unfortunately, there's some physical limitations around this type of connection. Number one, it needs to happen over fiber optics connection. So obviously to your mobile phone becomes a problem. Number two, there's distance limitations. Usually 200 kilometers is about the theoretical limit. 100 kilometers is sort of the practical area where people focus on. So we need to develop quantum repeaters. So these are new technologies that haven't been developed yet, but there's a lot of research going into doing those then. Or you can use ground-based telescopes to satellites for using transmission through the air. So those are options which you can look at then, but it's a lot of physical infrastructure around it. The quantum safe crypto route basically says, if the math that we use today is a problem, what's the new math? What do we replace it with? And of course, like all good math problems, we get to look at a lot of fun, different math systems that are out there then. If you remember, the crypto that we use in the commercial world today is built off of RSA, which is all about, it's really easy to multiply two prime numbers together, but it's really hard to factor that large composite number at the end if the numbers are big enough to do it then. Or the elliptic curve Diffie-Hellman problem, which is really about how do you add and subtract numbers inside a group, which is created on an elliptic curve. What we look at now in the quantum safe candidate space are some different math areas, and I can come back to these later on and get into a bit more detail about all of them. But something that we've been really lucky with in the world of RSA and ECC is number one, they're very fast. They're very small, and you can use them to solve a lot of the basic things that we need to do. So if I have an RSA scheme, I can use it for encryption, and I can also use it for signing. So for the authentication part of the system then as well too. In the case of the candidates that we're looking at for the new math, they're not quite as universal as that. Some of them you can use for both of those operations, but the keys are bigger, and they all have their own sort of specialness around each of them then, which is great if you're a math person, but a little bit more challenging if you're an implementer, like our company is then. But of course, cryptography is a language. So we all have to agree upon the language that we're going to use if these systems can work. If you think about a TLS connection, so I mentioned that Amazon connection before, you don't use it. If I'm at my browser, I don't use an Amazon client to connect to an Amazon server. And Amazon isn't running a special Amazon might be, but your standard website isn't running a special web server just for their environment then. You're using Chrome, you're using Firefox or Safari, or maybe you're using Edge, maybe you're using Internet Explorer if you work for some organizations, but the clients are diverse. And then the servers you connect to, maybe you're connecting into Apache, maybe you're connecting into Nginx. Like there's all of these different backends that you're going to connect to as well too. And so we can't rely upon them to all implement crypto correctly. We have to specify the crypto that we're going to use then. And NIST, so the National Institute of Standards Technology in the States, they're really the organization that focuses on setting those standards. And they started in 2016, so they're coming up on about 5 years into their standardization process right now. They're in round 3. They've kind of narrowed things down to a shortish list. They started with over 80 candidates at the very, very beginning. We're down to about 15 right now. Candidates in the round 3, we're going to then, the outcome of that round 3 will be a couple that will be standards, and then there'll be an additional round to standardize a few other things. So we're kind of, the light is at the end of the tunnel for specifying what the new math is, and that allows us to start looking at how do we integrate this into all of our systems, because of course crypto isn't just about the math. As I said before, the math is extremely important. We have to make sure that it is as solid as humanly possible, that it's fast and efficient and difficult for someone to attack. But the way we use the crypto then ends up being specified by lots of other standards groups all around the world. The IETF is responsible for setting how the internet works. So TLS, all of our different IKE and IPsec, I'm just thinking of the crypto, the security related standards, X509, they think about all of the different frameworks that we use for connecting on the internet, and they specify those. You have Etsy, who looks after things like 4G and 5G and 3G and all of those cellular systems there. They all use public key crypto, so those need to be updated. You have X9 for finance. You have ISO for pretty much everything out there. I2T, which is really looking at more telecom-oriented standards. And there's more and more. This is just a very short list here, but it points again to the scale of the IT effort going on internationally to get ready for those new quantum safe solutions that are going on. And then think about it from you as someone working in an IT environment. All of the products you use are going to need to be updated to utilize these new systems. So what to leave you with out of here? For your organization, you really need to start thinking about three things. So number one is start thinking about how is quantum safe going to affect the products that you use? Is it products that you build yourself, in which case then you're going to be thinking about this from the point of view of I'm a developer and I need to look at what's my roadmap for updates to my system, or maybe it's going to my OEM partners and finding out what their roadmap is and when they want to bring in systems. Step two, never let a good crisis go to waste. This is a good opportunity to recognize that this won't be the only time we have to make a crypto change in our infrastructure that we have deployed. So this is a great opportunity to start thinking about how can we make future changes easier. So this is this kind of buzzword of crypto agility, but thinking about how you actually will make those types of changes in a safe way in the future. When it's like home renovations. When you have the wall taken out and you're looking at all of the electrical, it's a great time to also look at the plumbing because you have everything open and you can upgrade the installation at that point, and it's much simpler and much less mess in the future if you can do all that before the drywall mud comes back up then. And finally, down the road, you're going to be looking at actually implementing quantum safe solutions in your environment. Again, these might be things that you're implementing yourself, or there might be things that you are just buying from the vendors you work with then. So with that, like I said, something completely different for everyone then, but encourage everyone, if you want, reach out to us at ISARA Quantum Safe, or hit me up on LinkedIn, and I'm happy to chat with everyone then going forward.
A question for you, just from my own side of things. I know that you kind of talked about car manufacturers and stuff, and I think Tesla, probably one of the biggest and sexiest car manufacturers out there at the moment. One of their, I was looking at some of their cars, and basically all the difference is from their, say that, I don't know, the Model 3 to the Model 3X or the 3X1 is basically software. So, and this speed is quite rapid from the base model to that kind of higher level model. What are some of the I guess problems that these companies will face when they start to have people trying to breach their devices in the cars?
So that idea of doing, we'll call it aftermarket feature enablement. That's well known in the computer industry. Then, if you think about, I'll give you another example. If you remember back in the old days when we didn't take photos on our phone, and you would have this thing called a camera, and we had DSLRs. DSLRs, you have the professional models that might be $5,000-$10,000 that you would kit out with high-end lenses. Then you'd have maybe the entry one. If you think of a Canon, like a Rebel, sort of the entry-level one. Those have the same sensor inside of them, but it is software which is going to then specify what features are being enabled or not. And if you think about it from, say, Canon's point of view, there's a huge amount of money that they have this stand to lose if someone can easily hack that and enable those features then. Just similarly, Tesla, you mentioned, I can buy ludicrous mode as my aftermarket then to safely drive on Ontario highways. But, again, like this is, and I mentioned to you about that $33 billion for the auto industry. That is partially because of feature enablement. The other half of that is that, half of all car recalls that happen are software related. So there's a huge cost associated with it there. But as there's more and more focus on people having access to these systems, and if they know that there's a way to bypass the organization's protections there, and that lets them get an improvement for free or little cost, then there's a huge driver for it then. And so organizations need to be very, very strong on not just the math. I like thinking about the math because that's a neat area then, but it's the whole system. What's my software engineering processes that I'm using? How do I know that the all of the say open source libraries that I'm integrating, I'm using the most up-to-date ones? When there's patches that need to be applied, how do I make sure those patches are applied? Like there is, if you're familiar with the idea of an SDLC, so secure development lifecycle, it thinks about that. A secure product starts with with the requirements for the product then, and then the design, and then the implementation, and then the testing, and then the in-market support. And that all of those things, it's a whole life cycle, and you have to do all of those right to have a product that's hopefully secure.
Given the recent hack on Florida water systems, how would this be applied to protecting infrastructure? Example, SCADA, IoT devices, etc. Things that control things like mixing valves.
Yeah, and that was a scary hack that came out. If I remember correctly, they were able to bypass or gain entry via VNC server. So this is things like remote desktop access. Then, what it really points to, number one is how fragile a lot of our critical infrastructure really is, especially when parts of it end up getting connected to the internet when maybe they shouldn't be connected to the internet. But number two is, I'll harp a little bit on that whole SDLC side. A lot of those SCADA systems are very old, 30, 40 years old. And so they're not using the most up-to-date machinery and the most up-to-date software inside of them then. But there's an entire field around how to write software for safety systems. And there's also a field on how to write software for secure systems. And those two things are necessary, but not sufficient. So you have to kind of do both of them when we're thinking about those types of environments then. And one of the challenges we get into is you think about, let's say the software that's running in something like a Raptor fighter jet. There is an enormous amount of scrutiny that goes into every line of code that goes in there. And even then, there might be 5 or 6 million lines of code. A Ford F-150 might have 140 million lines of code inside of it then. And part of that is because there's going to be hundreds and thousands of ECUs, so electronic control units inside that pickup truck that all have software running on it. They might have Unix or some other operating system that's running inside there. And all of that needs to have patch management. All of that needs to make sure that, those are more and more of those are getting connected to the internet. And so they have to be, hardening has to be a core thought in terms of how you actually deploy any type of software in those environments.
Can you comment about the NSA quantum computer project? Is it truth that they are working on that? Ooh, NSA quantum computing. Let's go.
Yeah, so if I remember correctly, that was part of Snowden's revelations, was that NSA is doing work in quantum computing. That shouldn't really be a surprise because every government around the world is doing work in quantum computing, or at least all the very large ones there. And that doesn't necessarily mean that it's secret work that's happening. Often the work that a government will do is actually funding work at the various universities around the world then. If you look at, we'll say the UK government, the UK has this whole kind of quantum hub idea then. So all the various universities will have different focuses. So you have quantum sensors, which will be in one specific area. You have the quantum computing, you have quantum algorithms, you have, I mentioned QKD, so quantum key distribution, and then quantum safe crypto, which is the area that I like. And they're doing it as very much a public-private investment where they're putting in, I think it was about 250 million pounds for the previous 5 years. So this is going on all around the world. Every government is. They're also doing work in looking at, I mentioned that harbors and decrypt issue then. That isn't just one government around the world. Governments around the world are storing encrypted communications. This is well known, and there's been a number of different findings talking about that then. So it speaks to that, there's a lot of great economical reasons why people want to have a quantum computer. There is also some nice things from an intelligence point of view, but let's not forget, one of the reasons that Silicon Valley has such a disproportionate reach into the rest of the world was because their ownership of digital computing. So when digital computing started, you had the entrepreneurial investment, you have the academic investment, and then all of the VCs over time as well too. And every country around the world wants that same Silicon Valley, but for the quantum industry. And so there are national and regional drivers around the world to try to ensure that your area becomes the quantum valley of the future.
How do you think quantum computing will affect banking and blockchain cryptocurrencies? Are existing cryptocurrencies vulnerable to attack and theft?
Yeah, it's a good question. So there's a couple of ways that quantum computers will impact blockchains. And I'll speak broadly of blockchains, not like Bitcoin or anyone specifically then. So if you think about how crypto intersects with blockchains, so we have one in the context of things like proof of work. If you think about what is Bitcoin built, the enduring thing of Bitcoin is the largest hash calculating computer in the world. Whenever someone is trying to do mining of quantum computer or a mining of a new Bitcoin, what they're actually doing is trying to invert a hash function. So specifically SHA hash function in that case then. So quantum computers can be used for breaking hash functions, but that's really not what they're great at then. You can use Grover to do that then, but as I mentioned before, that's a bit more expensive than we really thought it would be. Where it becomes more interesting is in the context of, say, my private key that I've associated with a wallet. So that's in the case of things like Bitcoin, it's going to be ECDSA that we're using in there. So for my signatures in there as well too. Also, if we get into privacy enhancing blockchains, they use things like snarks and other kind of cool crypto math constructs there. Those are quantum vulnerable, but there is work into building quantum safe versions of those different types of snarks that are out there. And this is work. If you look at Ethereum, one of the things they've been doing in Ethereum is how do they make sure they're ready for moving to quantum safe algorithms? So if I'm talking to someone in the finance space, the big takeaway for them is think about the crypto you're going to use in your blockchain, because most people haven't actually deployed them. They're still in kind of the fun research stage. Think about the crypto you're going to use and think about the migration path. You don't want to have to fork your blockchain in order to bring in a new crypto scheme, because that can become a big problem. Just look at Bitcoin Classic and all of those things that are out there.